In this video, we're going to look at modeling this conwhip system that we talked about in the previous video using Simio. So for those of you who didn't see the video, recall that conwhip is constant whip, and the basic idea is that we keep a constant amount of work in process in the system at all times. So in this system, which is called the penny fab, from the book Factory Physics, we keep 4 penny blanks in the queue and 1 penny blank being processed. And so the signal, when a penny finishes, the signal is sent to introduce another blank into the queue. And so under this strategy, we will have 1 penny being processed and 4 in the queue at all times, hence the name constant whip. And in this case, the conwhip number is 5. And there are some interesting characteristics of this system relative to the queuing systems that we've looked at previously. First of all, there are no external arrivals. Instead of external arrivals, we have internal arrivals that are caused by completion of a penny. So in this case, completion causes the arrival of the next blank. And then also we have, to simplify things, we're going to have deterministic processing times. So deterministic processing times, oops, that doesn't look very good. Let's try that again. Deterministic processing times of 1 minute. And what we're after is theta is equal to the expected value of time in system. So we want to know what's the expected value of the time in system at steady state. So there are a couple of interesting aspects of this model pertaining to modeling in this in Simio. First of all is this notion that there are no external arrivals. Instead of external arrivals, we're going to use this signaling mechanism where the completion of 1 penny signals the arrival of the next blank into the queue. So instead of having just a standard source object instance that creates entities according to an in-arrival distribution, we're going to use a different mechanism. Secondly, we want to look at how to observe this transient bias. Recall that's what we're after here, is understanding the transient period prior to steady state, the bias that can induce in the performance metrics, and then how to mitigate that using a warm-up period. So to start our model, we're going to use our standard single server queuing system. So we're going to have our source, our server, and our sink as we've done before. And then I'm going to connect these up using connectors because I don't want there to be any transfer time. And so when I connect all these, and then I'm going to grab my model entity, and then as usual I'm going to click go just so I can periodically observe what's going on and make sure that I understand what I've done. And so I've just created, using all of the default parameters, a single server queuing system. And so we can see these external arrivals coming into the server, being processed, and then departing. Of course, for our system, that's not really what we want. What we want to do is we want to create this conwhip system, or a constant whip system, where we have 4 entities in the queue at all time and 1 entity being processed. Okay, so before I talk about how to do that, let me go to the server and just set it to our deterministic 1. So we just have a deterministic value rather than a observation of a random variable here for 1 minute. Now the key here is on the source. When I look at the source properties here, we have several different arrival modes, and what we've looked at previously is the inter-arrival time, where we just specify the distribution. In this case, we don't want that. What we want to do is we want to use the on event time, and you can see when I do that, it immediately comes up with a warning, or an error in this case, that says, okay, well, you've specified an event, but you haven't given the event name. And so we've highlighted this event name. And so what Simio is waiting and saying, okay, well, you want to create an entity whenever a simulation event occurs. What event would you like? And so we need to have an event associated with the completion at server 1. And there are numerous events that built into Simio, or built into the standard library that we can use. But what I'm going to do is I'm just going to pick the input at sync 1. So here's my input at sync 1 entered. And so that says when the entity enters the input station associated with the sync 1 object, that's the event that I want to use to trigger a new arrival. And so I also need to initialize the system. So my initial number of entities will be 5. And so what happens, oops, let me go back to that. When I run, the source object will create 5 entities immediately and then create subsequent entities when one of the entities leaves the server and enters the input station for the sync. The last thing I'm going to do is I want to only look at the first 10 pennies, right? So I'm going to have maximum arrivals as my stopping condition of 5, right? And so it's going to initially create 5 and then subsequently create 5 more. Each time one penny finishes, it creates one, and then the simulation will terminate. And so now when I run, you can see immediately I have my 5 pennies. And as time advances, let me kind of speed this run up a little bit. Let's make this 5, for example. We can watch, that's still not very fast. Let's try this again. Make this 25. And now we can see the system, the last penny left. And so it's kind of hard to see what's going on there. So let me run it one more time and say we have our, oops, let's see, reset. We have our 5 pennies, 1 being processed, and then we can see 1 departing every minute. So let's look at the performance metrics of our system. Before we do that, we need to talk a little bit about the run length. Since we're only running for 10 pennies, we need to decide, well, how long is this run going to take? And that's where this nice deterministic processing time really helps us out, because we know that each penny is going to take 1 minute. Therefore, the time required to process 10 pennies is going to be exactly 10 minutes. So I can go to my runtime and say, let's just make the run length exactly 10 minutes, and we'll know that we will finish, let's see, at exactly the right time. And so now again, when I run, you can see that we've processed all of our pennies, and here we are at 0.17 hours, which I hope equates to 10 minutes. So now when we go look at our results from our interactive run, we see that the flow time, which we're interested in, is 0.0667 hours. Again, difficult for me to do time units in hours, so I'm going to switch that to minutes. And we see the average time in system is exactly 4 minutes, which is precisely what we got in the previous video when we did this simulation manually. Now, when we look back at our system, recall that we know what the answer is, right? This expected value of the time in system at steady state, it will be exactly 5, but in our first 10 pennies, we got 4, and that's caused by this initial transient period where the first penny only spends 1 minute, second penny spends 2 minutes, third penny spends 3 minutes, fourth penny spends 4 minutes, and so those are all downwardly biased. And so when we compute an average based on that, instead of getting 5, we get 4. Before we look at how to use a warm-up period, let's just add one more thing to our animation, or to our model, that's going to illustrate this issue a little bit clearer. And so what I'm going to do is I'm going to grab a status plot here. There we go, just put a status plot, and then I'm going to name this average time in system, and I'm going to specify my time. I'm only interested in operating for my 10 minutes, so I have a 10-minute run, right? And so I have my 10 pennies, as we said before, are going to take exactly 10 minutes to run. And so I pick my expression now that I want to model. And let me, oops, I stopped the model. That's why it's not giving me the expression editor. So I go to my expression, and what I want is the average time in system. So I'm going to say default entity population, population, oops, time in system average, right? So what I'm going to plot is over simulation time, what is that average time in system? And so what we then expect to see is when the first penny finishes, that average time in system should be right at 1, and then it should systematically increase to the value of 4 once we finish the run. At least that's what we hope to see if we did this right. Okay, so let's go in our model, and now we see the simulation going, and oops, I've got that in hours, so let me go back one more time. That wasn't what I expected. I expected to see it jump up a little bit, and so let's just multiply this, multiply this by 60, because Simio computes values like this, or time values, using hours internally, and so we can just multiply that by 60. And now when we run, we hope to see that increase. Here we are starting at 1, as I said before, and then we systematically move up until our average after the final penny leaves is exactly 4. So at this point, we've replicated our model, and we've done some simple experimentation. First of all, we observed the results, and then we created this status plot so that we could watch the results being created over time, and we got the results matched our expectations. So at this point, we're pretty satisfied that we have modeled our system correctly. And so now what we want to do is look at how to mitigate this. Of course, as we said, our objective is the expected time in system at steady state. And so when we just look at this time in system plot, we can clearly see that we haven't reached steady state, or that we have incorporated the initial transient period, I should say, in our calculation. And so in order to do that, I need to create an experiment, right? So I'm going to stop my model, go back to Project Home, and create an experiment. And you can see that I'm just going to at least start out with the default experiment where I run 10 replications, right? And we can just simply run that and look at our 10 replications, each of 10 minutes. And then when I go to Pivot Grid, I see, again, exactly what I expect. Again, we're interested primarily in this flow time. And so I look at the average flow time is 4 minutes, the minimum's 4 minutes, the maximum's 4 minutes, and the half width of the confidence interval is 0, which tells me that I have exactly 4 minutes for all 10 of our replications. So what we need to do is we need to say, okay, I want to ignore the first 5 pennies, or I want to ignore at least the first 4 pennies, as we showed in the previous video when we developed this methodology by hand, right? And so what I'm going to do is I'm going to go to my experiment properties and look at this property called warm-up period. And what I'm going to do is just specify that I want to warm up for 5 minutes. Okay, I want to warm up my model for 5 minutes, and let me then reset and run, and then we'll talk about what's going on. So I run for my 10 replications, and now when I go to my pivot grid, I have my flow time 5 minutes exactly. Again, confidence interval of 0, so it's exactly 5 minutes. And so we have effectively chopped off or eliminated the observations during the transient period. And so specifically how this warm-up period works is Simio starts running at simulation time 0, and it runs until it reaches this 5-minute period, and then it flushes or resets all of the performance metric counters. So all of the internal counters for the performance metrics are reset to value 0. But the entities in the queue and their arrival times and all of that stuff is maintained. It's only the performance metrics that are reset. And so the net effect is we are only tabulating results after the warm-up period starts. And of course, as I said, we get exactly what we expect of 5 minutes. So in this case, what we've done is we have taken a very simple model with the penny fab and use deterministic processing time so that we can have some expectations, so that we know exactly what should happen, and now we've replicated that in our simulation model. And then introduced a warm-up period. So go to our experiment. We introduced this idea of a warm-up period to then remove or to ignore the information during this initial transient period so that we could get what we're after, which is the performance once we have achieved steady state. Of course, in this case, we have a very simple system. Again, we looked at 10 pennies. We have deterministic processing time, so we essentially know their answer before we actually do this. So we don't really need to do the analysis. However, when we introduce stochastic components, if we have stochastic arrivals and stochastic processing times or more complicated flow, then it's going to make the task quite a bit more difficult. However, the difficulty really comes in determining what this warm-up period needs to be. The process is the exact same in that I create the model, I initialize the model, and then I set the warm-up period to be approximately once the system has reached steady state. Again, the difficulty here is going to be figuring out what that time period should be. And as we said in the previous video, if we estimate that value too low, then we still have that bias, the initial transient bias, If we introduce, or if we set the warm-up time to be too long, then we have removed all of the transient bias, but we've thrown away usable data, and that usable data, throwing away the usable data, is going to impact that confidence interval, and so it might force us to run longer. So having a warm-up period too long is clearly the conservative approach, because you get the correct answer, you just might have to do more work to achieve that. And so that general idea is a topic for another video.